little bit today. We might even get a little bit into comparison. So, as you know, I like to kind of personify this a little bit and think of these series as someone that we're encouraging and cheering for to do well. Just by a quick way of review, the first thing we looked at, the nth term test. That was the really tough, mean coach who would only tell you if you're doing something wrong. Remember, that nth term test or the divergence test will only tell the series you diverge, and if it's going to converge, it just doesn't say anything. Then the next one was the more balanced, fair coach, geometric series test. Very fair, very informative. In fact, very informative, more informative than some of the other situations we found. So remember, the geometric series test is only focused, it has a very narrow focus, right? It's only focused on geometric series. So good coach, but very narrow bandwidth as far as what they can do. And then last time we looked at the integral test, and the integral test is also very fair. It'll tell a series when it converges or tell a series that it's going to diverge. There were three big conditions for the integral test. Do you remember what they were?
Positive, continuous, and decreasing.
Yeah, positive, continuous, decreasing. We spent some time talking about that graphically. But then really the integral test, even though it's fair and has these conditions and everything, seems like it's going to work pretty well. It has another really important condition that really narrows its ability to help us. What is kind of the big narrowing factor?
We have to be able to find the integral.
Yes, you have to be able to actually anti-differentiate that nth term of the series. If we don't know how to do it, it's not going to help us. Sir?
Why can't it be negative, continuous, and increasing?
So you're going to find out about the negative. So like
So instead of it going like this, I went like this.
So if every single term is negative, is what you're saying, then what we would do is we'd factor the negative out of the sigma, and now all the terms are positive.
Okay,
What we're going to find though is that some series will, and we've seen some of these already, go. So here's the x-axis. They go positive, negative, positive, negative, positive, negative, and that introduces a whole other situation. And so, yeah, if every single term was, if it was x-axis, negative 10, negative 5, negative 1, negative 0.1, negative 0.01, negative 0.001, if they're all negative, we'd factor the negative out, and now they're all positive. And so we'd still be able to use the integral test in that situation. Yeah, for sure. Okay, so then I am going to say that the two tests we're going to look at today and practice with today, these would be, have you ever had that coach that always, has a way of putting it? They have like a little phrase or something that just makes you get it quick. You know what I'm talking about? Like it's deep, it's good, it's correct, but they just have this little phrase that helps you get it quickly, perhaps, right? And maybe you can think of one of those coaches or one of those phrases that helped you, right? And so these other two ideas, these two kind of tests we're going to look at are kind of like that. So the P-series test, if you can get it, is quick and very, very helpful potentially. And then I think probably the more helpful, the one that you're going to use more often than not, is what we call the harmonic series, and what the harmonic series is and what it does and how it all works. We can tie these all together with the integral test, but I'm going to tell you like the quick phrase of P-test or harmonic series. It's going to be very, very helpful. Okay? Oh, I forgot to turn my phone off. My little phone lady is telling me someone's calling me. I'm so sorry. I'll go turn it off here in a minute for you, Meg. So let's talk about the P series. So it's up there. It says the P series is of the form 1 over n to the P, where n, of course, is your variable of summation, and P is some power. And that's why this is called the P-test, power, because it's focused on the power. So I would say that the P-test is extremely helpful and can make your life much easier, and it's very quick. But I think the P-series is incorrectly overused. So let me give you an example of something that is a P-series. I'll give you a specific example. So a P-series would be something like I'll just write it here. Sigma of 1 over n squared. That's a p-series. Sigma 1 over n to the 1/3. That's a p-series. First one converges, second one diverges. Yep, we'll get to that in a second. Or you can already see it coming up here. Let me give you one other example here. This, however, is not a p-series. Right?
The basic form.
So the p-series is specifically 1 over n to some number. And that's it. Now, if we did see something like this, we'll learn of other ways to deal with that later on. It's really not that hard to deal with. But that's not a p-series. So you can't look at the thing in red and say, oh, it's a p-series and p is 2, blah, blah, blah. It's not a p-series. Can't do it. Just because it's not a p-series. Okay, so the p-series test, the abbreviation for that, of course, is p-test, which everyone jokes about, yes. It's a p-test, right? This day and age of doping and steroids and such, it's a p-test, yes. So, it's kind of in a bad spot right there. Let me, Meg, are you on PEDs for your soccer?
Yeah,
No?
that's
Yes?
fine.
Okay. Okay. We were all assuming that because you can hardly move. Yeah, I get it. Anyways,
Oh, I got you.
here's the P-series test in a nutshell. This is why I say this is that phrase that if you know it is very helpful and you can cut through real quick and it's not too bad. If you can identify it as a P-series and P is bigger than 1, converges automatically.
Wow.
But if P is less than or equal to 1 or between 0 and 1, then it diverges. Of course, think about this. If P were negative, you'd flip it up and what would you use? Nth term would not go to 0, right? So that's why we say 0 to 1 on P, because obviously if P was negative, we wouldn't even consider this. We'd just say, hey, nth term for divergence tells us all we need to know. So if you think back to those examples I gave earlier, sigma of 1 over n squared, hey, P is 2, and that's bigger than 1, so that series would converge. Sigma 1 over n to the 1/3, well, P is between 0 and 1. That series would diverge. So can you see how this could be very quick? All you have to do is look at it, say, hey, that's a P series, and I see the P, and you write your answer.
Just a question, how does the integral test help us?
So how does it help us? Well, so in one case, let me go back to that last example that I showed you. Let's say you had 1 over n squared plus 1. So this is, the nth term test will be silent because the terms are heading towards 0. It's not geometric. And it's not a p-series. And we'll find out in a second it's not harmonic either. So at this point, the only thing we could do with this is hope that the integral test will work. And this is integrable, so the integral test would actually work. And I will say that the integral test is basically the foundation of why the p-test works and why the harmonic series ideas work as well. So I would say most of I personally think the integral test is often quite awkward because there needs to be quite a bit of reasoning and steps to go along with it. If I could use the harmonic series ideas or the p-series test, I would do that in a heartbeat because I could just look at it and say, p-series, answer. I'm done. So I don't think we'll use it a lot once we have filled out all of our ways that we can look at these. But it is the foundation. It's the reason why these tests even work.
Doesn't that converge to pi?
If you do, so what we looked at before was integral from negative infinity to infinity of 1 over n squared plus 1. It does converge to pi. We did this exact one.
So how would it be negative?
So he's talking about the improper integral we did back in like November or something. We did that exact improper integral. Yeah, so for a series, we would not start at negative infinity. We'd start at like 1 or something like that.
Oh, right.
Yeah. Yeah, that's one of my favorite integrals of the year. It's so awesome. Love it. So then the harmonic series is, I put here a specific form of the P series. And if I show you this, if you look at this right here, and you say, okay, yeah, I get it. It could be thought of as a specific form of the P series, with P being 1, right? A general form, like a generic version of the harmonic series, your book puts this out there. Some math books don't say this. And since our book does, I go ahead and throw it in. They feel that 1 over an plus b, where a and b are just some numbers, like 1 over 5n plus 6 or something like that, is a general form of the harmonic series. So I thought maybe we could prove this one to ourselves. So let's look at it like this. I'm going to use the integral test for this. If I have integral of 1 over an plus b, and I'm going to go from 1 to infinity, I would put this, right? I was going to do an integral test on just this general harmonic series. There should be a dn in there. There we go. So this would equal the limit as n heads towards infinity. And wouldn't this be 1 over a times ln of an plus b? Wouldn't I need an extra factor of a in the numerator? Make the antiderivative head towards ln? Okay. And then it'd be evaluated from 1 to b, of course. Darn it, I've got 2 different b's in there, don't I?
Make it C.
This doesn't make any sense. I'm going to make this be a c. There we go. Now it all makes sense. Okay. So now it would be limit as, and I put n on that one too. What's the deal here? There we go. Limit as b goes towards infinity of, and it would be 1 over a times ln of ab plus c minus, it's the alphabet, 1 over a ln of a plus c. Okay, so that second term doesn't have any b's in it, right? That second term, so that's not going to matter. But the first term does, right? It's got ln of ab plus c. So we've actually dealt with this before. If b is heading towards infinity, and then you multiply that by a, and then you add c to it, and then you do the natural log of all that, where are we heading?
Infinity.
We're heading towards infinity. And then infinity minus whatever that is, still just heading towards infinity, right? And so we can say that this diverges, that this definite integral diverges. And then from the integral test, you know that if the definite integral of that series nth term diverges, then we know that the series also diverges. So what we've done here basically is a baby proof that the harmonic series always diverges. If it's a harmonic series, you'll always get that ln, right? And as ln's input heads towards infinity, ln's output heads towards infinity as well. So here's the big takeaway. Harmonic series always diverge, period. Unless it's an alternating harmonic series, but that's different. So if it's just a regular harmonic series, just harmonic, then it always diverges.
Would 1 over 3n plus 2 be harmonic?
Mm-hmm. According to your book. There are other books that say no, it just has to be 1 over n.
So in terms of our understanding, it is?
Yeah, and you'll be good. The AP test is not going to try to split hairs on that because they know that some authors disagree.
Why do they disagree?
That's a great question. I don't know. I've never sat in on any of those arguments.
Because, I mean,
What
goes to
argument
infinity.
is-
Because what they would say, so someone who's in favor of this would say, well, look, this 1 over an plus b thing works if A is 1 and B is 0, we agree, essentially, right? And so I can see that point. I don't see any point in saying, oh, no, it's not. So I think I'd fall in the camp of like, okay, I'm okay with calling that a harmonic series, but some people aren't.
Wait, it's just,
Like I said, I've never heard the other argument, so I'm not for sure.
Yeah.
is it just the convention of calling 1 over n a harmonic series? Is that the only argument? Is that the only-
No, it's the argument. So I think everyone agrees that 1 over n is a harmonic series. I don't think anybody would say anything different about that. It's that some people are a little more liberal and they would say 1 over 5n plus 9 is also harmonic, and other people are a little more dogmatic and they would say no, it has to just be 1 over n, if that makes sense. So nobody's going to argue with you about 1 over n being harmonic. Like everyone would agree on that, I think.
What's the definition of harmonic?
So yeah, so it comes from so it has its long old derivations in music. It really does. I don't know exactly who made that connection and named it that. Maybe there is no one particular person, but
How would that be the P series if there's a plus B?
so that's the I never called this a P series.
But if that's how they're called harmonics, a P series, and that's a harmonic, and that's a P series.
So I totally understand what you're saying, and this is maybe where the argument comes from. But I think this is where we want to be careful about like not overextending. Like, well, if this is this, then this is this, then this is this. That's why I pointed out some authors disagree, and this is probably part of the point of disagreement. The P series though is not just restricted to with P being 1, and that's where the issue comes in, right? So if P is 2, 3, 4, 5, well, now no one would agree with you. And so I think we would be making, essentially making policy based on one anecdotal, one little situation. And I don't think that that's ever particularly good. So does that make sense? Your question is fair, and that's probably part of the disagreement that people would have.
No, I just
I agree.
if I see 1 over 3n plus 9, I probably wouldn't easily recognize that as a harmonic or P series because that's not what the form looks like for P series.
Yeah, so P series can't have any plus this or minus that's. And no one's going to disagree on that. It's just this where people are going to disagree. And maybe the apparent inconsistency that you just pointed out, maybe that's why some people want to be more dogmatic about it. So if you want to be dogmatic about it, it's okay. It's not going to matter for me. There's always going to be a way through. You just have to use something else. You have to use an integral test or something like that. So there would always be a way. I'm okay if your conviction is that, do it that way.
Okay.
You can still be logical about it.
Fair enough.
You can.
You're wrong.
My way is the only way.
Absolutely. That's how life works.
Depends on who has the power, right?
Oh, come on. You know it's me.
So let's flip ahead to number 2. Number 2 could be done in several different ways. And this is like Santi, honestly, and frankly, number 3 could be done in several different ways. And so this is why I'm not going to say in most cases there's not just any one way. Some cases we might find, okay, yeah, there's really only one good way to do this. But in many cases, there's going to be more than one way. So can anybody identify one way that you could do number 2?
That harmonic series is
So
Let's go to that route.
here's all you got to do. This would be the easiest way. You'd say, this is a harmonic series. You have to identify it as such. And then you'd say, or really, frankly, you could just say, series, therefore, it diverges. That's really all you have to do. That's accepted math. Like we all know, or you're coming to know, that all harmonic series diverges. So if you can say that it's harmonic, you know it diverges.
If I just did harmonic and an arrow pointing to diverges, is that...
So I'm a fan of complete thoughts as opposed to snippets. Most of the time, on the AP test, the readers are instructed to be a little bit more liberal. So that might be taken on the AP test, but I would like to have a complete thought, just so I know that you're not just taking a shot, like you're taking the time to write a sentence. My sentence isn't that much longer than what you wrote, but I would favor a sentence or a complete phrase.
Fair.
So let's say for some reason you did not notice that it was harmonic. Whatever, it's okay. Maybe you could do this. You could say limit as n goes towards infinity of 1 over n. What am I doing? Nth term test. And what do you get?
0.
Oh, what does that mean?
Nothing.
Nothing. So I might have tried that. Do you see what I'm getting at here? I'm not going to try to just like pigeonhole you into you have to do it this way or you have to do it that way. You might try a bunch of different ways and find some of them productive, some of them unproductive, but you'll figure it out. You'll figure it out pretty quickly. And again, what if somebody did not see that it was harmonic? Could they use the geometric series test? Why not?
It's not geometric.
It's not geometric. Remember, geometric is numerical-based variable exponent. That's not this. What else could they use? There's at least two other things they could intelligently... Integral test, yeah. So you could say limit as b goes towards infinity of the integral from 1 to b of 1 over n dn. And then you'd get limit as b goes towards infinity of natural log of n, evaluator from 1 to b. And then you could say limit as n goes towards infinity of ln of b minus ln of 1. Oh, thank you. I keep doing that. And so what do I get here as a result?
Infinity minus 0.
Yep. So here, so we'd say because 1 over n is positive, continuous, and decreasing, and the integral diverges, the series also diverges. So you got to get those conditions in there along with your steps. So you can see, I'm sure you can see right away, just by volume, wouldn't the purple method be nicer, more efficient with your time? The red way works. What's the final way we've learned? Yeah, so we would say sigma from 1 of 1 over n is a p series, and p equals 1, which is, this is a little awkward because I don't think I'd ever do this. I would say 0 is less than 1, which is less than or equal to 1. Or you could put a p in there if you wanted to. Therefore, the series diverges. And of course, you'd label that reasoning the p-test. So you could have used the harmonic series concept, you could have used the integral test, you could have used the p-series test. Any one of those three would have worked. Clearly, in this case, purple's best, right? There's no getting around that, but any one of them would have worked. I'm wanting you to see this as holistically as possible. I don't want you to just see it as a bunch of choppy, compartmentalized, unconnected things. I hope I'm somewhat being successful. Okay, question?
Unless you give us like a kind of unsolvable integrals, the integral test will always work, won't it?
As long as you can find its, so as long as it meets the conditions, and you can find the antiderivative, yeah, I think so. We're gonna quickly find some where once we start introducing factorials and other combinations of things, that's going to become very problematic.
Yeah.
But in a lot of cases, yeah, it would work fine. It's a pretty powerful tool to use. Yeah. Okay, so why don't you check out number 3? And I'm open. I really would be open here on number 3 to using potentially a variety of methods if they work. So check it out. See what you arrive at. Sigma 1 over n squared plus 1.
Can you take me through this thing again to get pi?
Oh.
Out of this?
Yep. Well, so we're not going to get pi out of this.
Oh.
Because this only goes from 1 to infinity.
Oh, that's why I was confused.
Yeah. So where you can derive pi from
No, I just don't know what it means.
is specifically this.
Some, what do you think I was?
Like if you, so like this graph,
I gotcha.
this graph looks like a hill,
Yep.
I think, something like that. And so if you accumulate all the area from the left side to the right side,
That's when it's
and you've got to use limits, of course, that's when you get pi.
So,
Yeah.
For this one, the arctan of b as b goes to infinity. What?
So there, it's helpful to know the graph of arctan. So, and this is where the pi comes into play too, right? So here is a graph of tangent. So tangent, you've got vertical asymptotes, interval of pi, right? So this is negative pi over 2 for that one, pi over 2 for that one, and you're right, you have the right direction, looks something like that. So then arctangent, of course, is the inverse, and inverses are a reflection across the line y equals x. So, you think about that line right here. So you got to think it's still going to go through the origin.
Yep.
But then, if I've got this diagonal line and I reflect these vertical
It
lines,
just switches the concavity of it, doesn't it?
Oh, I remember this now.
I guess, so, yeah, sort of, you could say it that way. But the vertical asymptotes are really key, right? So this gets reflected to be a horizontal at pi over 2, and this gets reflected to be a horizontal at negative pi over 2. And then your actual graph, I guess the concavity change does switch, because this goes from concave down to concave up, and this is the reverse, right? So then as we go to the far right edge of the graph, we'll be cozying up to this horizontal asymptote.
Yep.
And if you went way to the left, and then you could maybe see with those asymptotes being what they are, you can see where pi would come about if we did that other integral.
Yep.
Right? So that's it.
Gotcha.
That's where it comes from. Yeah. So all those, I don't know, all those teachers that tell you, oh, you can just always use technology to graph. I'm like, sort of. But it would be so helpful if you weren't so reliant on it, right?
Yeah.
It is. Nobody's going to deny it. It's awesome. It's handy. It's very useful potentially. But if it gets to the point where it's handicapped you to where you can't think graphically or recognize something graphically, then I think it's bad.
I mixed up cotangent and arctangent when I was thinking about that.
Oh, okay, gotcha. Yeah, because then we'd be shifted off, a bit, and yeah. All right. So, hey.
Arctan kind of looks like a phase-shifted logistic graph.
Yeah, it kind of does.
Is that the arctan graph?
The one in red is, yeah.
So so there's a limit. It's pi over 2.
Yep. So I'm assuming the fact that y'all asked me about arctan, you guys use the integral test.
Yeah.
And that, I think, on this one is the way to go. So you'd go limit as b heads towards infinity of integral from 1 to b of 1 over n squared plus 1 dn. So arctan comes into play right about now. Arctan of n, evaluator from 1 to b. And then this is where you do your FTC1. I got the b right that time. That's good. Arctan of b minus arctangent of 1, like so. So then with this, I'll just come down here, I'll put it. So here, this was the main thing, knowing the graph, right? So as b heads towards infinity, arctan of b heads towards pi over 2. And then minus, what's arctangent of 1?
Pi over 4.
Pi over 4. So we end up with pi over 4 here, which that in and of itself is sort of an interesting result. So what that means, this is totally beside the point of series.
Oh, that's
So
a
if you
quarter of the,
If you start at, this is so fascinating, I've never really thought about this. So if you start at 1 and you collect all the area going that way, apparently you get pi over 4. So no, of 1 over n squared plus 1. Well, sorry, over here. Sorry, I was looking at the wrong graph. So thanks for correcting me because that's the wrong graph. So all of this area is pi over 4. So knowing what we know from what we did with improper integrals, what's this area right here? Pi over 4. Interesting. So like half the area is just on this one little part. And then the other half would be that whole tail going.
oh, right, because it's symmetrical,
Way
so
out
it'd be
here.
the same the other way, too.
Exactly, yeah. So So from negative 1 to 1, I guess we'd have to speculate that area would be pi over 2.
Why is from 0 to 1 pi over 4?
That's so cool.
Well, because I know I know from before, from a long time ago, if I do from negative infinity to infinity, the whole thing is pi.
About half.
Oh.
So that tells me from 0, because of symmetry, from 0 to infinity would be pi over 2. So if from here over is pi over 4,
Then it has to be pi over 4.
yeah, we're just
deviation.
we're just subtracting out parts of it.
Can you
just gets
explain
different.
how arctan of b is pi over 2 again?
So, and we're doing, the limit is b heads towards infinity. So as the input for arctan, and we're using this graph now, right? So as the input for arctan gets bigger and bigger and bigger, what is the output doing? So we've got a horizontal asymptote governing that. So as the input goes from 1 to 2 to 10 to 20 to a billion to a trillion to a gazillion to a whatever illion, we're still just cozying up to this pi over 2.
But let's say I forgot the graph. Is there a way to do it algebraically?
You can make a table. My little million, billion, gazillion thing, you could just make a table. And hopefully you'd be well versed enough, seriously, in the decimal, you'd make it on your calculator, right? And you'd say, wow, okay, the outputs were 1.2, 1.5, 1.54, 1.55, 1.56, 1.569, 1.5, hopefully at some point it's like 1.57. So this is getting a lot, really, really close to something I do know about. Oh, maybe it's pi over 2. That would be the only hope, I would say. Because tables are never going to give you a perfect answer. They'll just get you to see the pattern. But if you didn't really recognize it, it'd be tough. So this brings up a really important thing for us to put here. Two things. So first of all, you'd say, because 1 over n squared plus 1 is blank, blank, and blank.
Continuous positive and decreasing.
Continuous, positive, decreasing on the interval from 1 to infinity, the interval we care about, and the integral converged, then we know our conclusion is, therefore, the series also converges. And here is where people will go too far with this. They might say, therefore, the series converges to pi over 4, and that's where you're wrong. It doesn't do that. I don't, unless it's linear in some way. But I just don't think that would even ever work. Anyhow, I don't think we're ever going to get that perfect convergence where whatever the integral converges to, the series converges to as well. So don't take it to that point. We just know that if the integral converges, then the series will as well, and we leave any actual sums alone. Okay.
You have to say the interval from 1 to infinity.
I think that's best practice, because if you just said 1 over n squared is continuous, positive, and decreasing, that's not always true. Like if you just left it at that, in this case, right? Because this is the graph of 1 over n squared plus 1. So there are parts of that graph that are increasing. So it is always continuous, and it is always positive, but there's a part where that graph is increasing. So I think if you're going to make a declaration like that, we want it to be true. So, and you should be safe just including the interval that we care about, the 1 to infinity on this case. How we doing? I'm trying to not go too fast. Hopefully I'm not going too slow. Okay, fair enough. So number 4. This is where hopefully your intuition with series and some of these tests that we've talked about would come into play. When you look at number 4 and you start to think, what are my what are the weapons I have in my arsenal to handle these things? What jumps out to you? P-test. And that's the way to go. Totally the way to go. So we'd say this is a P-series. And P equals what? So if I just write that, it's not wrong, but it's not enough. I need to relate that 4/3 to why is 4/3 so important? It's bigger than 1. That's right. So I want to say P equals 4/3, which is bigger than 1. Therefore, the series does what? Converges. And that, guys, that's all you need to write. You need to identify it as P series, tell me what P is, and how it relates to 1, essentially. And done. What do y'all think? I mentioned earlier, you will use the harmonic series, and then later on we'll find out that there's an alternating harmonic series as well. You will use those a lot. Okay, so we used it a little bit here. You will use that one for sure a lot. Okay, so then why don't you guys explore with number 5 and see what this one does for you. I think it's the last one in this little set. Yeah, so number 5. Figure out what's going to work best and try that. So I know where Peyton is. Does anybody know where Justin is today?
Can I do this? I'm just curious. Can I say like a lot of plus and square equals
So no problem with that. I'm not sure what that is.
because it's, sorry. So since 1 over 5 is
Oh, that's your substitution. So, okay, gotcha. That's your substitution. Like I would say mathematically, there's nothing wrong with anything you've done there, but you do have a major problem because you've got an n on the top and a u on the bottom. So if you wanted to fully substitute this, you're going to need to handle that n. And there is a way to handle that. I can show that to you if you want.
But wouldn't it be just like n equals the square root?
Yeah, I think you would find that in the end, doing it that way, and that's, again, not wrong, except for the plus or minus that would need to be there, and then you decide that. It's gonna, although not illogical, it's not gonna be very helpful. If we're gonna do an integral test here, and we did want to use substitution, you want to handle, if you handle the dn would actually be also your key to handling your n. That would get everything substituted out pretty quickly.
I wasn't trying to do substitution, I was just trying to, because I was trying to see like, if I could do like n over anything like that. I don't know, I was like,
Yeah, it's like trying to simplify it a little bit, yeah. Yeah, I don't think there's a way to do that logically. I could be wrong, but I don't think there is.
just curious.
Yeah. Curiosity is always fun.
Curiosity killed a cat.
Thankfully, there's no cats in here, as far as we know. You never know. Because we're just trying to figure out the convergence or divergence of this. Have you guys arrived at a place where you think, all right, I have to use such and such?
Yes.
I think you do have to use the integral test. I do. I agree with that. So see if you can use it. This will be your last chance today to practice with that. So
Is this the right justification?
let's see here.
Or, like, I know, the answer might be wrong, but I just want the
Yeah, so-
wording that I use.
So the wording graph is positive. I don't know. I think that's okay. Graph. Positive, decreasing, continuous, and the integral diverges. Therefore, the series diverges. Yeah, I think that's pretty good way of putting it. I do. One word about your integral up here, though. When you flip this up, this should be negative. Yep.
Thank you.
That's a pretty common
Yeah.
thing.
Yeah, no, I knew that's what you meant. I was just, I might be confused a little bit. I don't know what it is, so I gotta say now.
You guys almost have matching shoes. First
Yours are
glance, I
cooler.
thought they were. She's got the black part of them.
Yeah, she's the dope one. I have,
How's it going? Going okay? Are you Jamie's making you sleepy, Sam?
Yeah. I have my wheel pants and fuzzy socks, what else do you need?
I know, that's what I'm saying. It's like you're going to fall asleep on your feet. If you stand in line for lunch and you know, just goes off.
They said I'd get a letter in the mail in about a week or so.
Really? Exciting.
for Penn State?
Yeah.
They have brownies in the bistro.
Oh, big facts.
Or not the bistro, in the cafe.
No, you're trying to distract all of us now.
Show us the
Well,
phone.
I have flip too, so we'll see if it's mine. Oh, that was a quick
Santi's a
flash.
liar.
Santi is a liar.
Do they push out notifications about we have such and such here and there?
In the comments.
But does the app push notifications, or do you have to open the app?
Comments in the comments.
Okay.
They put it in the app.
They have nachos
Pretty
in these
nice.
They stopped putting, they have a chili dog?
What's for chili dog?
Yeah, salt nachos and the chips,
I
brownie.
had cereal on it.
I got macaroni and cheese tomorrow.
Is the chili dog in the comments?
On school, yeah.
It is.
I'm not
They have
really.
baked macaroni and cheese.
Salt and pepper
Black
Well, then I
cherries.
email Steve in the car.
Wait, I need
Hey guys, let's
I'm like still kind of.
gentlemen, let's wrap this up. So with the integral test, did you guys go here?
Yeah.
So you needed to fix Timmy's mess up, or you needed to do substitution, one of the two.
We also needed another 1/2, right?
Another, well, once I do my antiderivative, there will be an extra factor of something in there, for sure. Yeah. So then, when you do your antiderivative, you end up with 1/2 times, it would be 1 plus n squared to the 1/2. I think it'd be times 2 though, Jack. Divided by 1/2, aka multiplied by 2.
Yeah.
Okay, so limit as b heads towards infinity of, it would be 1 plus b squared to the 1/2 minus 2 to the 1/2. So what happens with your limit here?
There's infinity.
Right, basically infinity square rooted, or it's infinity squared plus 1 squared. We're talking about infinity. So then we'd say because the graph of this thing is positive, continuous, and decreasing on our interval, and this would be, again, an example of where mentioning the interval is really a truth or false proposition, because if I say it's just positive, continuous, and decreasing, I think we could find that the graph of that is actually negative sometimes, right?
Yeah.
Whenever n is negative, I think we'd have negative outputs. So just want to put the interval there. And the integral diverged. Therefore, the series diverges too. And that, of course, that sort of logic is using the integral test.
Are you ever gonna give us like one of these where it's not positive, continuous, and decreasing all with infinity?
So Peyton sort of asked about that yesterday. So I don't think that anybody's going to expect you in the course of like some multiple choice question or even a free response question to, without a graph, just know that, right? But I would say that I could see, and I don't know, I haven't written one of these myself for the College Board or anything like that, but I can definitely see how someone could write a question in which they're testing your knowledge of those. So they would say, maybe they'd give you some series, and they'd say, well, this series, as currently stated, does not fit the conditions for the integral test. Which of the following reasons, or which of the following things could be true? And then you'd have to parse those out and decide how the conditions apply. So I can see that being a question, but I don't think it would be, and then show that the series converges. That's just too much for any one question. So, yeah, it's fair. Anybody else? So you've already built a lot in a very short time. You've learned about the nth term test, the geometric series test, the integral test. You've learned about the p-series test. You've learned about the harmonic series. It's not really a test, but how the harmonic series nature. You've already learned about all those things. Okay. So I want to introduce a little bit about what we'll be doing on Friday. So these two tests, yeah, we got a couple more. I'll just tell you, there's comparison tests. There is the alternating series test, and then there's the we'll use this a ton. Oh, the ratio test. So we've got several more. We're a little more than halfway done with these. We do have several more of these to go. So to continue the coaching analogy, and this is not a real reach here, this is always a hard really, this would always be a hard thing to hear, but can you imagine if, Santi and Nick were on the same team, and I said, Santi, why can't you be like Nick?
Oh,
Nick is so awesome at blah, blah, blah.
Isn't he?
What's wrong with you? I mean,
that's a heartbreaker.
it's not a really great coaching move, because now you've set someone up almost as like an idol, and then you've told this other person that, well, you are always going to fall short. You're not going to measure up to this person. This is not a great coaching move. There's a fine line here too, because you could always say, check out Logan, he's doing so awesome. Look at how hard he's working. Like you can almost use the positive thing too, but you have to be careful with that as well, because that can go bad on you quickly if you're not careful with that. So these two coaches are all about comparing, honestly.
Oh.
They're going to say, well, hey, look. Hey, check it out, Meg. This function's higher than this one. Therefore, blah, blah, blah. Or, oh, look at this function. This one's lower than that one. It's comparing. Like, literally, it's that coach that compares. It's comparing. So it's not really a healthy thing. But thankfully, Sam, I'm not exactly sure why you're packing up. Jack, I'm not exactly sure why you're packing up. There's 5 whole minutes left. Or, no, 3 whole minutes left. I'm going to use all of them. So if you'll agree to not pack up early, I'll agree to not start early and mark you tardy because you didn't show up early. Fair enough? Okay. So the comparison tests, there are 2 of them. The first one is a direct comparison. And like this is what you think. It's literally saying, hey, Santi, why aren't you as good as Nick? Like it's direct.
Wait, can you get that on recording?
Oh, I'm recording this.
Oh,
this is on the video.
Take it out of context.
But you might be taking it a little bit out of context, yeah.
my favorite sound.
But it literally is just that clear. It's like, hey, function, you're lower than that one, therefore, blah, blah, blah. Or, hey, function, you're higher than that one, therefore, here's my conclusion. It literally is that direct. The other one's a little more sophisticated. It's called the limit comparison test, and it's a little more subtle than, hey, Santi, why aren't you as good as Nick? It's not that direct, but it is still a comparison. Nick, why aren't you as good as Santi? I mean, just to balance this out a little bit. Yeah, sorry. What's that?
Don't lie.
Egg. This is all being recorded. This is going to be on YouTube forever. So when you guys are like 40 years old, you could maybe somehow search this out and be like, I remember that one day Mr. Anderson said Nick was better, and whatever.
Yeah, this was the defining high school career today.
So, guys, I want to give you just a brief, we'll revisit this for sure, but I want to, listen please, I want to give you a brief graphical treatment of this. And I want to just look at these first 2 bullet points right here. I will represent B with red, and I'll represent A with blue. So here's how this works. Notice it says 0 is less than A, which is less than B. So B is always higher, right? So if I have these 2 graphs drawn out, so B is always higher, so B would be up here, and blue, say, would be down here somewhere. I'm oversimplifying it somewhat, but let's just say it was something like that. So here's the comparison test right here. If B converges, remember B is the higher one, so if the higher series converges, doesn't that mean that the lower series has to also converge?
Yes.
Because remember, it's just a question of how quickly are we getting towards 0? Okay. But then if the lower, this is the second part, if the lower series diverges, then wouldn't the higher one have to also diverge?
Yes.
We're comparing. We're saying, hey, blue graph, you diverged, and red, you're higher than that? You diverged too. That makes sense? Fair. Red, you converged. Nice job. And blue, you're below that? Well, you converged too. So we're comparing graphically, essentially, is what it comes down to. So I mentioned here you can't flip that around. It just simply doesn't work. You'd have to think of some other things here. The challenge you might find with these is thinking of something to compare to. That could be the challenge sometimes. So we'll work on that on Friday. So hope you guys have a great rest of your day. See you tomorrow for the polar quiz.
Stop,
Wait,
stop,
what's the
Nicholas.
quiz tomorrow?